All right, Prop 39 says equal triangles which are on the same base and on the same side are also in the same parallels. So it's kind of like the reverse direction of the two previous propositions that we proved. Well, I guess it's more so the reverse direction of 37, but it's related to 38 in any case. So the idea is we're saying that if we have, and I've drawn two different diagrams, so if you just look at either one, it's the same diagram either way. I'll show you in a second why I drew two diagrams, but the idea is if we have two triangles, ABC and DBC, where they obviously share the base BC and they're on the same side of BC as each other, then if those two triangles are equal, if ABC equals DBC, the claim is that if we connect AD, that AD will be parallel to BC. Right, and the way that Euclid goes about this, they only list out sort of one diagram. They do one diagram and they make it a without loss of generality kind of proof. But I think that it benefits from having sort of two different diagrams. The logic works either way, but I think that it makes more sense to fill in the details. That's kind of why I like doing this, is trying to fill in some of the details that were sort of left to intuition back then. All right, so proof. Assume triangle ABC is equal to triangle DBC. And I'm sure it's clear, but again, just as a reminder, when we say, like here, when we're talking about this equality, we don't mean congruence. We mean that they have the same area. Even though I sort of inadvertently, again, drew ABC to, they look congruent to me. That was just an accident. I didn't mean to do that. So instead of congruence, we're just assuming that the areas are the same. And we want to prove that AD is parallel to BC. So, claim, first, we need to join AD. So I'll do that. And can you guess? We need to prove that AD is parallel to BC. That's kind of a tough thing to prove, is that two things are parallel. So rather than proving it directly, we prove it by contradiction. We assume that they're not parallel, and then we work with the resulting logic until we run into some kind of contradiction. And that's what we'll do here. So we'll just say join AD, but assume I'll say, suppose AD is not parallel to BC. Well, if AD is not parallel to BC, then we know that there is some line that passes through A and is parallel to BC. So, and let me just read what Euclid says, or what's written here, because I again think that there are some details left out that should be filled in. So he says, let AE be drawn through the point A parallel to the straight line BC, and let EC be joined. But what's not sort of stated there, and it's only becomes apparent when you sort of move further through this proof, is that the point E is intended to fall somewhere on BD. So, to be a little bit more precise, I might say, draw the line L through A such that L is parallel to BC. So that's the first thing that I'll do, and then I'll say let E be the intersection of L with BD. Yeah. And here's why I drew two different diagrams, because there really are two different cases here. The first case is that E falls somewhere inside of ABCD, this trapezius. The second case is that E falls outside of it. So, right, and I should say produce BD if necessary, which is what we'll do on this one. So this first one we'll assume, I'll say here is our point, or here's our line L, which we're assuming is parallel to BC. Oof. And we'll assume that this point right here, where L crosses BD, we'll say that's E. Kind of a cluttered diagram, but yeah, I think you can read it. So yeah, and then over here we'll assume that E falls outside of ABCD. So I'll just kind of make this line here. And we'll assume here's our line L passing through. Just going to try to make it so I don't go through D, the label D, if possible. Yeah. So here's our other line L, and here's the point E. Right. So there's E, and then join EC. So in either case, we're going to join EC. And let's see, I guess maybe I'll do that as a, should I do a solid line or a dotted line? I'll do a dotted line, just to maybe keep things from getting too cluttered up here. I don't know, this actually might make it more cluttered. We'll see. So we need to do EC on both of these. There we go. Okay. Yeah, it's not clean either way. I think even if it was a solid line, it wouldn't be particularly clean. Yeah, so we joined EC. Right, and I guess I should have justified this step, drawing the parallel. Whoops. That's okay. That was proposition 31 that allows us to draw parallels. Yep. There we go. Whoops. Added in after the fact. It's fine. Okay, well, if that's the case, then since AE is parallel to BC, well, we would have that the triangle ABC is equal to the triangle EBC because they share a common base and they are in the same parallels. So ABC, then triangle ABC equals triangle EBC. Since they're in the same base, same parallels. Man. Where's all this smudging? Where's all of that coming from? I don't know. Where's all of that coming from? Alright. So, right, and that was Prop 37 that said that. I'll try to erase just some of these really quickly. Do they erase? Where are they coming from? Why? I don't know. Maybe it's sweat. I have no idea. Okay, so Prop 37. But we're given that ABC equals DBC. So if ABC equals EBC, ABC equals DBC, then we get that triangle DBC is equal to triangle EBC, the areas, that is. And just from here, Euclid says, well, that's a contradiction. He says, but ABC is equal to DBC, therefore DBC is also equal to EBC, the greater to the less, which is impossible. And that's where I want to just fill in a little bit of details. So I'll say, maybe this is diagram 1 and this is diagram 2. So in diagram 1, notice though that we can say that DBC is equal to EBC plus DEC. And that's where the contradiction comes from, because we just said, wait, DBC equals EBC, yeah, but now we're also saying DBC could be written as EBC plus DEC. And then in diagram 2, it's kind of the other way, where DBC falls inside of EBC. So EBC is equal to DBC plus EDC, which is, again, that's where the contradiction comes from. So I'll just say, but this is a contradiction. So, well, all of the logic in here was correct. The only assumption that we made that led to this contradiction was assuming that AD is not parallel to BC. And the way that Euclid sort of wraps this up is he says, similarly, we can prove that neither is any other straight line except AD. All right, he says, therefore, AE is not parallel to BC. But this is a contradiction, just to keep in line so with what Euclid wrote. So AE is not parallel to BC. And then he pretty much just concludes neither is any other line except AD. So AD is parallel to BC, which is what was required to show. So QED, therefore, etc.